One thing about this textbook that we do have this time is it is early transcendentals. So we'll go ahead and talk about exponential and logarithmic functions now, because those are going to be mixed in all throughout the course. Whereas in the past, we didn't do exponential and logarithmic till the end of Cal 1. So we're going to mix it all in. So today we'll go ahead and review what inverse functions are, exponential, logarithmic, and then the trig stuff. Review it a bit, and then then we'll get going again, like I said, on Wednesday with the calculus. All right, so let's look here. All right, so I'm just going to go through this quick, because this should be review. But first, we'll look at exponential functions. Okay, so an exponential function is a function of this form. Okay, and b is a positive real number, but not 1. Okay, because if b was 1, then that would just be a horizontal line. All right. It cannot be negative, because if it was negative, then whenever x was fractions, you would actually have complex numbers, and that's not exponential at all. Okay, so to be exponential, b has to be positive and not 1. Okay. Because b of x is defined for all real numbers, the domain is infinity to infinity. Right? And then because b of x is greater than 0, all values of x, the range of f is from 0 to infinity. Okay. And then, of course, b, anything to the 0 power is 1. Therefore, for any base, f of 0 is always 1 for an exponential function. Okay. Let's look at a graph here. All right, so here's some examples of the graph. So just notice all of them will cross at 1. So it has a y-intercept at 1. If this black one here is representing 2 to the x, what would happen is you would go out here and then it would just go up, up, up exponentially, right? If it's 3 to the x, you're going to have the same shape, just going to be pulled in a little more, go up a little faster. If it's 5 to the x, it'd be a little more. 10 to the x, whatever. So whatever the base is, as long as the base is bigger than 1, it's going to have that same shape. Okay. On your pages of graphs there, then that exponential function is drawn as just a curve like this, and it would be anything bigger than 1. The base would be bigger than 1. Okay. Now, if the base is between 0 and 1, so if the base is a fraction or a decimal, it still crosses at 1 there, except rather than going up on this side, it goes down that way, and then this would be a horizontal asymptote, and it goes up this way. Okay. Over here, the x-axis is still a horizontal asymptote, but that would be as x gets smaller. Okay. Any questions about that? Okay. Now, we do have a natural exponential function, and that is when the base is e. All right, so in calculus, you see a lot of e's. All right, so e's and natural logs. You don't see much with different bases, or logs with different bases. A lot with natural log and e, though. Okay, so we see that a lot. So natural exponential function is base e. E is an irrational number, and it is 2.718281828, blah, 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 blah. Okay. Repeats, continues forever without repeating. Shape of the graph is the same. Okay, so if the red one here was 2 to the x, and the blue one was 3 to the x, e to the x would be somewhere between the two. Okay. Now, one thing about e to the x, all right, y equals e to the x, is that the tangent line at 0, 1 actually has a slope of 1. Okay, and that's something later that will be, we'll talk more about tangent lines and things. All right, that's exponential. Questions about that? All right, inverse functions. Inverse functions, what is an inverse function? The inverse of the function, okay. All right, that's it. All right, what else? A little more. what does it sound like, inverse? Opposite, okay. What would be opposite? Okay. Okay. X and Y, you're swapping the X and the Y's. That's what inverse is, okay? So it's like you take the domain of one and that becomes the range of the other. No, I'm sorry. Domain of one becomes the range. The domain and range is swap, all right, X and Y swap. So given a function f, its inverse is that this is the notation, right, the little -1 symbol, such that whenever y equals f of x, then that is equal, then the inverse of y is actually equal to x. All right. All right, and then I go through this a little bit. Let's see, because the inverse undoes the original function. If we start with the value of x and apply f to it, then apply inverse of f to the result, we recover the original value. Okay, so if you take the inverse of f of x, you just get the value you plugged in to start with, x. Okay. Now, one-to-one functions, a function f is one-to-one on a domain D if each value of f of x corresponds to exactly one value of x in D. All right, now, what does that mean? Okay, well, we can always find an inverse. Okay, so an inverse, you just take the x's and y's and swap them. You can always do that. Okay, but when you swap the x and y's, do you have a function? Okay, so because for it to be a function, every x must be paired with only one y. Okay, that's not always true, right? So if you took y equals x squared, which is this, and you swap the x and the y's, you get this. What would the graph of this one look like? Sideways parabola. So you'd have like this, like that. All right. Is this a function? No. This has an inverse. This would be the inverse of it, but it's not an inverse function because every x got to pair with only one y. Okay. So a one-to-one function is just one where every x is paired with only one y and every y is paired with only one x. All right. So it has an inverse function. Okay. So how can you tell if it has an inverse function? Well, horizontal line test. All right, remember normally do the vertical line test to see if something has a function. So, or if something is a function. So like here I would do a vertical line test on this one and I would say, well, everywhere I do the vertical line touches the graph in one spot, it is a function, right? If I do a horizontal line test, does it pass a horizontal line test? No, because it crosses in two spots. So that means when I do the inverse, I do not have a function. All right. So we check with using a horizontal line test to see if something has an inverse or not. Okay. So let f be a one-to-one function on the domain D with a range R, then f has a unique inverse with domain R and range D such that that's true. Okay. Now, to find an inverse, you just swap the x and the y's, solve for y, and that's your inverse. Okay. This graph kind of shows what should happen if you have two things that are inverses. Inverse functions are just inverses. Is the two graphs should be symmetric about the line y equals x. Okay, so it should be true if the two are inverses. All right, so that leads us to logarithmic functions. Logarithmic function is just an inverse of the exponential function. Okay, and if we had more time, if this was pre-calculus class, we could talk more about that, how that works and everything, but we're just reviewing. So the log function is the inverse of the exponential function. Okay, and so if this is the exponential function, Then if you swap all the x's and y's, so this 0, 1 becomes 1, 0, you get that. This is what the graph becomes for the log function, okay? So the exponential function has a y-intercept at 1. Logarithmic function has an x-intercept at 1. The exponential function has a horizontal asymptote at y equals 0, which is the x-axis. The logarithmic function has a vertical asymptote, which is the y-axis at x equals 0. Okay? And then the same kind of thing goes on here with your bases. If you've got log base 2, then that would go up where this green one is at. Log base 5, same shape, just stretched a bit, would be through there. And then log base 10. And then what would be the base of natural log? What's the natural exponential base? E, right? So if you see ln, that base of that is always E. Okay? All right, any questions about that? Now, again, on your graphs page there, that got those little graphs on it, exponential function is drawn just like this. Okay? Now, if your base is a fraction between 0 and 1, it's going to just go like this. Okay? Same. You still have a vertical asymptote. It still has a x-intercept at 1, just like the other one was. So, and since these are inverses, the base, same thing is true for the base for the log functions as the exponential function. B has to be positive and it cannot be 1. All right, so any questions about that? So because the range of b to the x is 0 to infinity, all right, not including 0. So if you take an exponential function, whatever the base is here, say it's 2 to the x, you cannot make 2 to the x power equal 0 or a negative, no matter what you plug in for x. So the domain will be everything up to 0, but not 0, up to positive infinity. So that means when you do the inverse, the log function, the domain of it, x, can only be from 0 to infinity as well. So you cannot take the log of 0, you cannot take the log of a negative number because of that reason. Okay? All right, let's see. We can talk about all that later. Okay, questions about any of that? All right, let's see. A couple of quick little things here with logs we need to remember. Then we'll just do a few problems. Then look at the trig stuff. So sorry, skipping that. All right, b to the log base b of x power is equal to x. Log base b of b to the x is equal to x. Whenever we solve equations or need to do something with some of the expressions with log or an exponential in it, that's the two properties that we'll use usually. Okay, so again, when these are the same, it's just going to equal that x there. When those bases are the same, it's just going to equal x. So we'll use those. Like I said, whenever we have equations or things, we'll use that to solve those. All right, these are properties you really need to remember with logs. Anytime logs come up in problems, normally these are what you're going to use as far as doing the calculus or whatever that you're trying to do to it. So just notice here you've got a single log of a product. So you can write that as two logs with a sum. So if it's a product over here, it would be a sum of two logs. If you're dividing here, x divided by y, then you can break that apart with subtraction into two separate logs. Okay? Or the other way. If you've got log plus log, you can put those together as a product if it's addition. Of course, your bases have to be the same on all of them for that to work. So, and then L3 here, this is the power rule, which we do use that a lot. If you've got log base b x to a power, you can rewrite that with that power out in front of the log. Okay, so we definitely use that a lot. Log base b of b is equal to 1. Okay. Last thing, then let's look at some problems here. Change a base. All right, so let b be a positive real number with b not equal to 1, then this is usually the one we really look at, okay? So if you've got log base b of x, and I want to change that, so if I want to put that, say I've got log base 2 of 4, and I want to know what is that an estimate of, okay? Then you can take just the ln of the number divided by the ln of the base. So the ln of 4 divided by ln 2 would be the ln base 2 of 4. Okay. Or you could do the log of any base divided by each of these. All right, give you the same thing. Okay. Those we'll use occasionally as well. All right, let's look at a couple of problems here. Okay, so I'm going to go to this board now. All right, so first, a couple of questions about inverses. Where do inverses exist? Use analytic and or graphical methods to determine the largest possible sets of points on which the following functions have an inverse. All right, so just inverses first in general. All right, so say we have f of x equals the absolute value of 2x plus 1. Okay. Now, what will the shape of that graph be? V, right? V. So, going to be a V, all right? Now, notice we are adding 1 and multiplying by 2 there, okay? So, it would be shifted, okay? Where would this 0, 0 point be shifted to? You go to the left, okay? Now, this is one a little tricky. You need to write it like this. Okay, when you're multiplying by a number and have another number with it. So it is going to the left because it's a plus, but it only go over 1/2. So your vertex should be right here at 1/2. Now, another way to do that, if you just set 2x plus 1 equal to 0, that'll tell you where the vertex is at, either way. So it should just go, nothing else really matters. It should go up like that. Okay, something like that. All right, so, yes. That stretches the graph. It's going to affect your x's, so it's going to stretch it a bit. Just stretch it. All right. All right. So does that have an inverse? No. All right. But the question is, where does it have an inverse? Okay. So if you only started here at negative 1/2, so you could either go negative infinity up to negative 1/2. It would have an inverse here if you just look at the left part. Or you could say 1/2 to positive infinity. Either one of those, you would have an inverse just for that part. Okay? But not the whole thing. Okay?
On a test, do we have to put both for it to be correct?
Probably won't ask that on a test. Yeah. I think for my math lab for the homework, probably just put one of them. Yeah, I think just one. Yeah. So. Okay. All right. What about this one? Let's say we have f of x equals 1 over x minus 5. Okay. All right. So what is that one going to look like? See if I got the graphs here. On your graph page, I think I gave all of them out. Let's see. I'll get to number 8. If you look at number 8 on that graphs page, all you're doing is subtracting 1 from x, 5 from x. So that would shift that graph which direction? if it's a minus 5. Other way. To the right, yeah. So it's opposite, remember, if you're adding it to, if it's directly to x. So, yeah. So we go to the left. So normally you would have vertical asymptote there. So here we'll have it over here at 5. This. All right. And everything else is going to be the same. That's just going to be a rigid shift to the right 5 units. So you got this, and you got this. Okay, if I follow that. So where does that have an inverse? It is 1-to-1 everywhere. Okay? If you do a horizontal line test, it's going to work everywhere on this graph. Okay? So we could say F is 1-to-1 on its domain. So we would say negative infinity to 5, union 5 to infinity. So everywhere except 5, you would have an inverse. You would have a asymptote there as well. So, all right, let's see what's next here. All right, next it says find the inverse function on the given interval if specified. Graph both f and the inverse on the same set of axes. Check your work by looking for the required symmetry in the graphs. All right, let's do these real quick here. Okay, so we want to remember what is the shape of the graph. Okay, so looking at f of x equals 3x plus 5. What is the shape of that one? It's a line. Yes, it's a line, right? So this is just a line. Okay, y-intercept 5, slope of 3. So if I graph that, let me go ahead and graph that one. So I have y-intercept 5, slope 3. So rather than going up 3 and over 1, I'm going to go down 3 and back 1, just so I don't have to have such a big graph. Okay, there's that one. All right, so now I want to find its inverse. It definitely has an inverse. So what I would do, first let's write y in the place of the f of x. Okay, now I need to swap the x and the y's. And now solve that equation for y. So I get y equals x minus 5 over 3. Then I'm going to use my inverse notation. I'm going to write it 1/3 x minus 5/3, which is 1 2/3. All right, so that is your inverse. You could probably write 5/3 if you're doing this in my math lab. But okay. Now, graphing that one. Y-intercept negative 1 2/3. The slope is 1/3. So I would go up 1 over 3, which is about here. All right, so that should go just like this. Okay. So this would be f. This would be its inverse. And then notice these two graphs should be symmetric about this line y equals x. That's going right through there. Okay. All right, so let me go and graph that one first. All right, so what does the square root function look like? Top of a sideways parabola, right? All right, that's it. So remember, that's what it looks like. Okay, so then I've got this going on. Okay, so we got to shift it around a bit. Okay, so this is the weird one again where you're multiplying x by a number and got a number inside the function as well. So let's do this. And then let's do this. Okay, so the minus in front of x, how does that reflect the graph? When it's with x. Across the x or the y? the x-axis. Okay, so it's going to go across the x. If the negative's in front, remember it goes across the y. So if it's inside, so we go this way, and then what will the minus 3, how will that shift the graph?
To the right.
To the right 3. Okay, so 2, 3. I could go up to the left one, up 1, 2, 3, 4. All right, that would be the graph of that one. Okay. Now it's inverse. Let's go ahead and take it. I'm going to write y in the place of f of x. Okay, then I'm going to swap the x and the y's. So this will become x. This will become y. Square both sides. So y is equal to 3 minus x squared. Okay. Now, for this one that we started with, the domain was negative infinity to 3. Okay. The range, what would the range be for this function that we started with? What's the smallest this can equal over here?
The range be a negative infinity to 3.
Okay. Can a square root equal a negative? What does a square root normally equal? It actually can be either one, but not. We think of the square root function as always being positive, right? So really the smallest that this can be would actually be 0, right? If x was 3. If x, if this is a negative, you have a complex number. So 0 to infinity is what the range would be, okay? So now for the inverse of that, this then will be the inverse. Write it with the notation there. That's the inverse. So then for here, I need to swap these for the inverse. So that means the domain of this one will be from 0 to infinity. And the range should be from negative infinity to 3. Okay, so what does that look like? Okay, you've got x squared. What's the shape of x squared graph? Parabola, right? It's negative in front of x squared, so it's reflected across the x-axis. The 3 is just like a positive 3 added to it, which would do what to it? Up 3. Okay? So, but only from 0 to infinity. So what you would have would be 1, 2, 3. And then it would go down probably about right there. Just like that. And it's only that right side of the parabola because of the domain. The domain here's got to match the range from that one. All right, if you do graph y equals x, that's what you get there. All right, any questions about that? Okay, I'm not going to do the last one. Y'all can do it as far as the homework goes. I do want to do a couple of these rational ones though. Let's see. So I'll take these two. Let's just do find the inverse for these two. All right, just so we be sure we're good on the algebra, and then we'll look at the logarithms. So I'm not going to graph these. We're just going to find the inverse function. Both of these have inverse functions. So let's just find them. But now as far as the graphs go, you need to get used to what does the graphs look like. What's the shape of all these graphs? Those on that page I gave you need to be remembering what those are, because if you don't know that, you're going to have a much harder time as far as when we get into the actual calculus. So, all right, so we're going to do y equals. All right, and now we're going to find the inverse. We're going to swap the x and the y's. Now I need to solve that equation for y. Okay, so what I would do there is multiply both sides times y plus 2. Okay. Now distribute. And now I want to solve for y, so get the y's together on one side. So I want to go xy minus 2y equals negative 2x. Okay. And I want to factor out the y. Okay. And now to solve for y, just divide both sides by x minus 2. Okay, and then just rewrite this with the inverse notation. And you got it. Okay. Questions about that? All right, this one's similar, except you got x squared in this one. So what I would do on this one first is look at the domain and the range as far as this goes. Okay, I'm sorry, I didn't write all the problem down. This is for x greater than or equal to 0. Okay. So they told us in the problem the domain would be from 0 to infinity. Okay. So what is the range going to be on this one if the domain is from 0 to infinity? What is all the possible f of x or y values? Okay. Okay, what's the biggest this fraction can be? The largest it can be? What? 2. Because whatever value I plug in here for x, if I keep plugging in numbers that are bigger and bigger and bigger and bigger, that's going to make the denominator smaller, which gives me a smaller fraction. So when x is 0, I get 2 over 1, and 2 is really the biggest thing you can get for any of it, period. All right. So 2 is the biggest value, and everything is going to be smaller than that. So your range, now what is the smallest that it can be? Can you get a negative number in the denominator? No. All right, because that's always has to be positive, and a positive number plus 1 is always a positive number. Okay. So, all right, can you get, so what about 0? 0 is, can this equal 0? It can't equal 0, but it can equal everything up to 0, right? So it'd be like an open interval. It's not going to include 0, but everything up to it. So we would say the range then, 0 up to 2. That makes sense? Okay. So when I do the inverse, I've got to use this for my inverse. So algebraically, I'll just say y equals x squared plus 1. Swap the x and the y's. And now solve this. So let's do y squared plus 1 times x equals 2. All right. And then I can just distribute my x. Subtract x. And divide by x. Okay. So y squared. Okay. And then to get rid of the square, square root both sides. And normally I would write a plus or minus, right? But if I take these, the domain of this one should be from 0 to 2. So it's not going to be negative. So really it should just be the positive of that. 0 to 2. Range would be 0 to infinity. Sorry for the crookedness there. That would be the inverse on that domain range. Okay? Questions about that? Okay, so they give you a few problems here where you've got this expression with a log, and then they tell you what log base b of x is, log base b of y, log base b of z is. Okay? So you would have to use those properties to break those apart in order to figure out what those are equal to. And mainly it's just a property, because most of the time when you do something with logs, that's what you're going to do, is you're going to have to use the properties. All right, so let's look at a couple of these. So with the properties, I can break this apart. All right, so probably what I would do first is go ahead and say, well, I've got division there. So I can write that as two different logs with subtraction. So I would rewrite that as log base b, and I'm going to go ahead and write like this: xy 1/2 power log base b of z. So remember, square root, same thing as 1/2 power, right? Okay. Now I could use the power rule to get that 1/2 away. So I can move that 1/2 in the front. So I get 1/2 log base b of xy. Okay. Now, x times y, I can break that apart again with addition. So this would be 1/2 log base b of x. I guess we could do this. Let's just do parentheses here. Okay, so I've broken it apart. Now I can just say, well, log base b of x is 0.36. Log base b of y is 0.56. Log base b of z is 0.83. Okay, and then just add those up, and I get negative 0.37. Okay, any questions about that? All right, we've got a few equations. Let's simple log equations. Let's solve those just to be sure we're good with logs. So let's do the log ones first. All right, so solving the equation. Okay, so again, we had those two properties earlier in the notes, remember? So here, we want to solve for x. So let's use that first property, where since this is base 8, let's raise both sides 8 to both sides of this equation. So it would be like this. So I would have 8 log base 8 x power equals 8 1/3 power. Okay? And then the property says if I've got 8 to log base 8 power, all this is just going to be whatever that is. All right, so x equals, which is what we're wanting, and then the cube root of 8 is just 2. X is 2. Okay? Questions about that? What is the base if it's a natural log? E. So this would be e to the ln of x power equals e to the negative 1. E to the ln of x power is x. E to the negative 1 is just e to the negative 1. Negative exponents are fine if it's e. I think my math lab will be okay with that. If it's not, you can do this. There's a point to where we just say, forget it with negative exponents, they're okay. Okay, so I don't know that we're there yet, but we're getting close. But with e, negative exponents are fine. So, all right, so those are logarithmic equations. If we have exponential equations, okay. Now you could do both sides of the log base 7 power. That's not going to be helpful on this one, I guess you can still do it that way, but let's just do ln of both sides. Okay, so any exponential, you take the ln of both sides, that usually works pretty well. Okay. All right, here, if you have an ln of something to a power, remember you move that power down there in the front. So I have x ln 7 equals ln 21. Then divide by ln 7. Which notice this is really the same thing with the change of base formula. This is really the same thing as log base 7 21, which is what I would have got if I had taken the log base 7 of both sides. Okay, but if you have multiple, like if I had a 7x and something at a different base over here, that would not work. Okay, but if it's just one base, you can do it that way. Okay, this is how the answer was left. So, okay, questions about that? One more. This one, if I take the ln of both sides, I get that. And then if I move this down in the front, I get that. I would then go ahead and divide by ln 3. And then you just got two steps. Add 4, divide by 3. Then divide by 3. X is equal to ln 15 over 3 ln 3 plus 4 over 3. Okay? And again, that's the same thing as log base 3 of 15. You wanted to have it that way. All right, questions about that?
That one on the left,
Mm-hmm.
put it as ln 3, or would you keep it as ln 21 over ln 7?
It's not ln 3. Right, you can't reduce it that way. You could say ln of 21 minus ln of 7, but you can't just divide those there. If it was the ln of 21 over 7, you could say ln 3. Does that make sense? That would be ln 3. But this you can't reduce that way. Okay. Good question. Good question, though. Any other questions? The only last thing on here with the logs is just using that change of base, which we kind of did. Let's just look at this last one here. Log. So if I want to know what is a decimal approximation of log base 4 of 40. So in other words, 4 to what power gives me 40? Okay, well that's not going to be a rational number, all right? But we can just say ln of 40 divided by ln 4, all right? And then put that in your calculator. You get 2.6610. Okay. All right, questions about that? All right, that is a review of inverse functions, exponential and logarithmic. We got about 35 minutes. Let's do the trig ones. All right.